Okay, in this video we're going to quickly give an example of Fubini's theorem. So this is in the context of double integrals. Fubini's theorem says that if you have a continuous function, the double integral of a continuous function f of xy over a rectangle R. Let's say the rectangle is AB cross CD. This double integral is equal to the iterated integral. Well, it's equal to either of two iterated integrals which are equal. So this double integral of f of xy dA is the integral from x equals a to x equals b of the integral from y equals c to d of f of xy, so dy dx, and it's also equal to the integral if you reverse the order of integration. So if you integrate y with respect to y on the outside and with respect to a on the inside, so this is dx and then dy, you get the same thing. That's what Fubini's theorem says. There's more than one version of Fubini's theorem, but this is the simplest version. So let's do an example of applying this fact. So this is not a definition, right? I mean, this double integral is defined to be a limit of a bunch of Riemann sums. And these two are iterated integrals, right? Where you just evaluate the inside integral and then evaluate the outside integral. So this is sort of like the fundamental theorem of calculus because in the fundamental theorem of calculus, you're trying to evaluate this integral, and if you evaluate an antiderivative, you can use it to evaluate the integral. That's part of what the fundamental theorem says. And this is sort of the same thing. We're trying to evaluate a double integral, which is a limit of Riemann sums, and we're going to do it by doing two kind of regular integrals that you're used to from calculus. So let's look at an example. Let's calculate the double integral of 16 minus 3x squared minus, no, not 3x squared, just minus x squared minus 3y squared, where R is this rectangle 0, 3 cross 0, 1. Well, so by Fubini's theorem, this integral, let's call it I. This integral I is equal to this iterated integral. It's more typical to do dy and then dx. So, right, y goes from 0 to 1 and x goes from 0 to 3. So 16 minus x squared minus 3y squared with respect to y, and then that with respect to x. So let's do the inside integral first. So we have the integral from 0 to 1 of 16 minus x squared minus 3y squared with respect to y. And I think it would be a good idea for you to pause the video and see what you get. But I'm going to do it out. So this is equal to, and we keep x fixed, right? So you're going to get 16y minus x squared y minus y cubed, evaluated from 0 to 1. And this is going to be 16 times 1 minus x squared times 1 minus 1 cubed minus what you get when you plug in 0. And you're just going to get 0 minus 0 minus 0, which is 0. And this simplifies to 16 minus 1, that's 15, and then minus x squared. So the inside integral is 15 minus x squared. And now we have to do the outer integral, and we're integrating this from 0 to 3. So we're evaluating the integral from 0 to 3 of 15 minus x squared. And this is just an ordinary kind of Calc 1 integral, right? So the outside integral is always going to be an ordinary Calc 1 integral because you're only going to have one variable left. And so this is going to be 15x minus x cubed over 3, evaluated from 0 to 3. And then you plug in 3, 15 times 3 minus 3 cubed over 3. And then minus 0 is 0. And you're going to get 45 minus 9, which is 36. So the answer is 36. Okay, that's the simplest example of Fubini's theorem. One thing to note is that in this case, you can do the integral in either order. So note that can also do compute the integral with respect to x first, and then with respect to y. So it'll be, if you wanted to do it like that, it would be from 0 to 3 dx, right? 0 to 3 of the inside integral, and then the outside integral with respect to y will go from 0 to 1. Sometimes there are examples where, sometimes there are examples where one or the other is hard to actually calculate in practice because maybe the function is hard to integrate. So you might have a function that's easy to integrate with respect to y, so then you could do this integral easily, but maybe it's hard to integrate with respect to x, and so it'd be hard to do this integral easily, or vice versa. And so you want to make sure that you know that you can actually do either order, because sometimes one order, I mean, in theory, they will turn out to be the same number, but in practice, it might be that one of the integrals is hard to do, and the other one is easy to do. Okay, thanks for watching.